Great. My talk today will pull together a few different themes, as you can see on my slide here. And I organized it around first talking about air pollution and health issues, and second, I'll focus on climate change. So let's jump into it. Thought this was a good place to start. This was one of the headline-grabbing episodes that's happened in Beijing in the past few years. This was January 14, 2013. This is the view from space. At the bottom are clouds, but over the city itself, that's pure air pollution. Some of the stations within Beijing reported PM 2.5 levels in excess of 500 micrograms per cubic meter. For some perspective, that's 20 times the WHO guideline for outdoor air pollution. And this is what it looked like on the ground in Beijing on that day. Okay? And there's many other very polluted places in the world. I know many of you are concerned with air quality here in North Carolina. North Carolina isn't among the worst places in the world, but there are reasons for concern here as well. This is the Ganges River Basin, and going from India into Bangladesh, another satellite image, another one of the most polluted places in the world. Okay, so we've gotten an ability now to look at air pollution from space. We've learned a lot about air pollution, but we're still left with a lot of the same questions that have driven our field over the past several decades, such as what happens to air pollution once it's emitted? Where does it go? How does it transform chemically? What are the most important air pollutants for health? We know that there's relationships, from Antonella's talk, for example, between pollutants like PM 2.5 and ozone with health. But are there particular chemical components of PM 2.5 that are really driving the health impacts? So that when we look forward, the next coming decades, should we be regulating other pollutants, other indicators of air pollution other than PM 2.5? And what we'd really like to know is, what's the importance of different sources for air pollution and the health effects that they cause? And what would be the benefits of different actions or different policies that we might engage in? It was those set of questions that led myself and several other people, leading scientists around the world in air pollution, Dan Costas here, to put together an article, and this just appeared in Environmental Science and Technology last week or so. And I'll highlight some of the conclusions from that. Air pollution is underappreciated for its global health burden. And I'll show you some results later that back this up. Air pollution and its health effects are changing globally and will change in ways that are related to economic development, to air pollution regulation, but also, as we look into the future, ways that are interrelated with climate change through the sources of greenhouse gases and air pollutants that are shared, but also through policies that we might enact to address climate change and what effects those might have on air pollution. Another theme was what air pollution science can offer. New possibilities through new measurement methods of new chemical components. This can give us a better idea, better ability to now hone in on the most harmful chemical components within the PM 2.5 mixtures. We now have cheap sensors that can be widely deployed, satellites that look at the Earth from space, and models. This whole suite of new understanding and new possibilities needs to be adopted more and made more useful within the health community, and there's good examples where that's being done. And our last conclusion here was that there's a need for the communities that I represent from science, being I'm an engineer, so think of people with backgrounds from science, atmospheric science, engineering, chemistry, physics, to work better together with people like Antonella and the community that she represents, from epidemiology, toxicology, from medicine. Okay, so I think that article will be interesting to many of you. I'm an engineer and I'm a computer modeler, and what I'll show you are lots of examples where we're using computer modeling to inform decisions about air pollution and what air pollution means for health and the kinds of actions we might take to address air pollution. Just as a schematic here, just so people are clear, this is a three-dimensional gridded model wrapping around the world. I often work with global models. It takes as inputs meteorology and emissions, a chemical mechanism that describes the chemical transformations of pollutants in the atmosphere, and its output are concentrations. what we've done then in my group is to take health functions that come from epidemiology, from the kind of work that Antonella described, and then use that to drive health impact assessment. We also need global incidence data that, in this case, we get from the World Health Organization. This sort of describes the methods that we'll use going forward in my talk. The health impact function might take a form that looks like this, where we have a baseline incidence rate of many different causes of death, but it doesn't have to be death. It could be hospital admissions due to asthma or something like that. A concentration response factor that comes directly from epidemiological studies. A change in concentration, in my case, we'll be using models, computer models of the atmosphere to get this change in concentration, and an exposed population. And we want to map these so that we're overlaying the right change in concentration on the right exposed population. Okay, so gridding the results is an important part of our efforts. And we spent a lot of time gridding population. This is what global population looks like. Adult population, because we're often most interested in adult mortality due to air pollution. And then a bunch of different causes of death. So these are rates of deaths per year per 100,000 people in the population for different countries around the world. So we've gridded all this together so that we can combine it together to do health assessment. So for some examples of the kinds of work we've done, I led this study in 2006, so actually a decade ago now, it's hard to believe, where we looked at methane. So for some background, methane is an important greenhouse gas, but methane also reacts in the atmosphere to contribute to ozone. So methane is a very unique ozone contributor in that methane actually contributes to the global background of ozone. So myself and colleagues looked at that as a very interesting case. Could we make a case for controlling methane on a global scale for the purposes of improving health globally by reducing ozone? So taking methane out of the context of greenhouse gas and climate change management and putting it into the context of ozone air quality management. And so we put methane into our global model, simulated a 20% reduction, and found that 30,000 or so deaths would be avoided globally in the year 2030 due to this reduction. This was enough in cost-benefit terms to justify the 20% methane reduction from all sources globally. Okay, so the health benefits to the global population were enough to justify this 20% global methane reduction, apart from other benefits that you'd get, by the way, from slowing down climate change, which is an important problem as well. It turned out that we weren't really aware of this at the time, but I think this was the first time that anybody had used a global atmospheric model to drive a health impact assessment. Okay, and that was just a decade ago. Now this field is sort of exploding. There's a lot of people doing this kind of work. Okay. Another early example, this was the work of Susan Annenberg, who was my PhD student. We looked at ozone precursor emissions from different continents and their effects on health globally as well as within that continent itself. And the conclusion that we reached was that ozone from North American and European emissions causes more deaths outside of those regions than within. This was, again, a surprising finding and pretty policy relevant. When we consider, for example, that the EPA, when it evaluates the costs and benefits of actions it might take to control ozone, evaluates only the benefits to American population. We're missing half of the benefits. And of course, if every country were to do that, we would under control ozone or air pollution generally. One of the neat questions we've been able to address using this approach has been to just ask the question, how many people die prematurely each year all around the world due to exposure to outdoor air pollution? Our group was the first to use atmospheric models to address this. This was a paper by Raquel Silva, who's here, and she has a poster in the poster session if you want to talk with her. This was our second paper on this topic, where Raquel here used an ensemble of global models. These were models that were basically run for the purpose of informing the IPCC on climate change. This is climate change research. But these models also evaluate global ozone concentrations and global PM concentrations, and we use them here to get an estimate of this global burden of deaths due to exposure to outdoor air pollution. So for ozone-related mortality, we get about 500,000 deaths per year, and for PM 2.5 related mortality, 2.1 million deaths per year. I'll say some more words later to sort of put those numbers into some context. But you see also that among the many different models that we had access to, we actually get a wide variety of different results. And it turned out that the uncertainty of the net estimate here was actually greater from the spread of different atmospheric models than it was from the uncertainty in the concentration response function that comes from epidemiology. Okay, so that was an interesting finding. For ozone, this is what the global map looked like as the multi-model average. And we estimated about half of the global deaths were occurring in East Asia, which is basically China, as well as India. For PM 2.5, East Asia was half of the total. Interesting note, this figure was made on the NASA website. It's a picture of the day a couple of years ago. Okay. Antonella mentioned the global burden of disease study. It comes up with estimates that are a little bit actually greater for PM 2.5, but less than for ozone than we had estimated, but still pretty comparable. This is now the most recent global burden of disease study for 2013 that lists air pollution as the 5th most important contributor, I'll say risk factor would be the proper word to use, to global health. But look at the things that are around it. Tobacco smoking, high body mass index, think obesity, alcohol and drug use. Air pollution is the most important environmental risk factor for health globally. It shows up here higher than any other environmental risk factor. And it's sort of comparable with a lot of things that are probably more widely appreciated as being important for health. Okay? And I think that's an important finding and something that's pretty new within the last decade. It's only been in the last decade that the numbers have been this big for health. Globally, this is 5.5 million deaths per year that come about prematurely due to exposure to outdoor, or we'll say ambient air pollution. That's broken down into components here due to ambient or outdoor PM 2.5 pollution, household air pollution from solid fuels. Let me say a word about that. This is a picture I took in Mexico, in a rural part of Mexico. I had the pleasure of visiting this family and they made me lunch. This is where the woman, her name is Regina, cooks. She spends several hours a day within this kitchen. There's no ventilation in this kitchen at all. You can see that the walls of the kitchen are black, okay? And she and children will spend several hours a day within kitchens like this in Mexico and throughout the developing world, okay? And you can see she cooked the entire meal on this little stove there. She's likely exposed to concentrations every day that are comparable to the Beijing episode that I showed you at the beginning, okay? This is a huge public health problem that's not present really in the United States. It's in the developing world. But that problem here is this 2.9 million. Ozone here is 0.22 million. For some perspective, right, this 5.5 million deaths per year is about 10% of all deaths globally. About 55 million people die all around the world each year, so this is about 10% of all deaths globally. Okay, so it's a big number. What I've done here then is to look at the GBD study at the top for globally. This is the 7th most important risk factor for death. In East Asia, which is basically China, it's 5th most important. The household air pollution from solid fuels, which is this indoor problem, 8th most important risk factor for deaths. In South Asia, which is basically India, it's 2nd most important. And then I pulled out from the Global Burden of Disease study their estimates for the United States. They estimate 79,000 deaths per year in the United States due to ambient PM pollution. Ambient ozone pollution is 12,000 deaths per year. They put a 0 for household air pollution for solid fuels because that was, in their mind, sort of defined in this developing nation's context. It certainly is the case that indoor air pollution in the U.S. kills people, but not using the methodologies that were used by GBD. I've also shown here a few other estimates for the United States, one from our group that is comparable to the GBD's group, and this is from Neil Fan from the EPA, several of you probably know him, for PM and ozone. So this PM number is about 3% of all US deaths. So that's about 1 in 30 people will die prematurely. It's hard to say that air pollution causes them to die because nobody dies with air pollution on their death certificate as the cause of death, right? But it's a risk factor that contributes to that person dying earlier than they would otherwise. So imagine if we were to get you and 30 of your friends and put you all in a room and you had to decide, and you were given the information that one of you was likely to die prematurely due to exposure to outdoor air pollution over your lifetime, right? But you didn't know which of the 30 of you, and then ask the question that Chris asked, how much would you be willing to pay to avoid that happening? And you might be willing to pay quite a lot, in fact, for that to happen. Okay. Let's come back to some of our research then. This is continuing Raquel Silva's work. What we did then was we were not just interested in what is the total burden, but we wanted to divide that burden up into different causes. So look at the different source sectors, what types of sources are responsible for that air pollution, and that's what Raquel has done here. So we find that for ozone, transportation is the most important risk factor globally. I say most important cause of ozone-related air pollution-related deaths. But you see, looking at the maps, that the maps show the fraction of deaths due to each of the different emission sectors, that those maps differ quite a lot in different places. So transportation is really very important in the United States here, but elsewhere in the world, energy is very important, residential combustion, and commercial, a lot of household burning would be very important in places like Africa and India. Okay. For PM 2.5, it's a similar story. Now it's residential and commercial we estimate to be the most important for deaths, right? Most important, especially in places where there's household burning for fuel and cooking and things like that. Energy and transportation stand out as being very important in the United States. Okay. Raquel has also done some work where she's looking at future scenarios. These, again, come from the climate world, where they're looking at different scenarios of future emissions and what they mean for climate change. So we have these, what's called RCP scenarios across the bottom. RCP 8.5 is a world without greenhouse gas controls. RCP 2.6 has very stringent greenhouse gas controls. And we're looking here at future ozone-related mortality in each of these scenarios, again, using a multi-model ensemble. And it's a complicated picture with a lot of scenarios and a lot of things going on, but a lot of suggestions that the world is getting cleaner going into the future. And we did the same for PM 2.5. Okay. And again, we're finding that there's quite a big difference among the different, when we use different models. Okay. If we look at regions of the world here, this is in 2100 compared to today, with China getting quite a bit cleaner, right? The US and Europe are already getting cleaner. China turns the corner and by 2100 starts to get cleaner. But India and Africa are actually getting dirtier even in 2100 relative to today. What that was showing was basically the effect of future concentrations relative to today's concentrations. And what I've shown here is actually an estimate of global burden of disease and how that changes going into the future. With global burden of disease here for ozone and for PM 2.5 often going up, even though air pollution is going down. Why? Because population is going up. And actually, it's expected that the susceptibility of the global population to air pollution will increase through time. As people are basically, fewer people are dying because of exposure to, because of causes like infectious disease. Looking out over the century, they're living longer, meaning that by and large people are dying more because of the causes that are affected by air pollution. Okay? And that's what's influencing these results here. Okay. I said I would talk about air pollution and climate change. Let's turn our attention to climate change. And I'll start with the basics. Why? Because there's a constant onslaught of people questioning the basics of climate science, and it's important for us to take an opportunity in occasions like this to talk about what we know about climate science and how we know it. Okay, so I'll start with what's certain. This is a picture of John Tyndall, who in the 1860s, that's the 1860s, that was a long time ago, conducted the first lab experiments that showed that carbon dioxide, methane, water vapor are greenhouse gases, that they absorb heat in ways that other gases don't. So it's important to remember that we've known that greenhouse gases cause warming longer than we've had light bulbs. Okay. Greenhouse gas concentrations in the atmosphere are increasing, and it's unambiguous that this is caused by human emissions. And global temperatures are rising. So these are things that very few scientists, serious scientists, would question at all, right? Global temperatures are increasing, greenhouse gases cause warming, and greenhouse gases are going up as well. By the way, I included here 2015, which was an exceptional year globally because of the strong El Nino, but still sort of underlying this rising trend since about the 1970s or so. That's been pretty dramatic. Okay. That's not everything we'd like to know about the climate change problem. So climate scientists have used models to address the question, can we attribute the rise in temperature to human activities? And these were the results of the IPCC using the words that they used and the graph that they came up with. This is the observed change in temperature with uncertainty around it, the warming caused by CO2 and other long-lived greenhouse gases, cooling caused by aerosols. This is particulate matter air pollution, basically, on a global level, causes a small cooling effect that's actually very uncertain, one of the important uncertainties in climate science, okay? The net anthropogenic effect, if you add up basically the green bar and the yellow one, you get this orange that actually looks like it's not a perfect match, but it matches pretty closely with the observed. And then we look at natural factors here. We have no reason to think that there's been more or less volcanoes over the past century, or that the sun has gotten hotter or colder over the past century. And internal variability means just random changes within the climate system. These natural factors cannot explain the observed change in temperature. Human factors are a much better explanation. The IPCC chose these words very carefully to communicate their intention of the conclusion. It is extremely likely, they said, that human influence has been the dominant cause of the observed warming since the mid-20th century. Okay? Extremely likely is a pretty strong statement for scientists. But when we look into the future, right, we don't know entirely what the future is going to be like. So we have a possibility of different scenarios. But given any one scenario, there's a range of uncertainty that's given to us by climate science. So we don't know how the climate system entirely will respond to human-caused forcings of the climate system. But we have some clue, and we know, for example, in this case, that this uncertainty bar does not include zero change in temperature, right? We have pretty high confidence that there will be a strong global warming. And even this reduction has an uncertainty bar that does not include zero. Okay? So this takes really dramatic effort to turn the world's greenhouse gas emissions around and bring everything down and go to a carbon-free world. Okay? And in order to achieve that, we'll talk a little bit more about what is needed, but even in that case, we don't get rid of climate change entirely going into the future. Okay. June asked me to say a few words about Paris and what happened in December, and so I'll do that now. The Paris Agreement, in order to understand it, I think you need to understand a little bit about the backdrop leading up to it. About 20 years or so of attempts and, you could say, failures or partial successes of trying to get the governments of the world on board to do something about climate change, starting with the 1992 UNFCCC agreement, which the US was and still is a signatory of, in which nations of the world committed, was the language, to holding greenhouse gas emissions constant at 1990 levels, and that has not happened. The Kyoto Protocol then that the US signed but never ratified and never joined, and in 2001, which was the first year of George W. Bush's administration, we pulled out of the Kyoto Protocol. Our stated reason for pulling out of the Kyoto Protocol at that time, or one of them, was that Kyoto didn't include major developing nations, which is true. It did not require reductions from India, China, or other major developing nations. But the framework that was put in place and actually signed into law by the first President Bush set in place a principle that developing nations would not have to take action in the first sort of rounds of climate change action, that it would be the industrialized countries of the world that would take action first. Okay. Then came the Copenhagen pledges, leading everything up to the Paris Accords. And what happened leading up to the Paris Accords was really pretty dramatic in that the US approached China, worked, as I understand it, diligently with Chinese leaders to come out with a joint announcement such that the two largest emitters in the world of greenhouse gases pledged together to reduce their emissions of greenhouse gases. That set a framework by which other nations knew that the two biggest players were going to do something, and their commitments followed. Okay? So that the US played an important role in the design of the Kyoto Protocol, which in many ways was designed to appease the desires of the United States by providing all these flexibility mechanisms, though then the US pulled out of it. The US action to pull out of it held, I would say, other countries back from really taking action on climate change. But now the US, again, showing sort of a leadership role leading up to the Paris Accords. So what do the Paris Accords do? The first thing is they're not legally binding. And you might remember that I said that the 1992 UNFCCC agreement was also not legally binding. Okay? So that might give us a sense of being pessimistic about what might actually come of this. But it seems that there's a lot of buy-in by a lot of nations, and it seems that things might actually happen this time around. So the targets that were put forward are pretty ambitious to reduce emissions by most nations all around the world by 2030. These are voluntary commitments that each nation is coming up with, meaning that if they don't meet those targets, there's no legal consequence other than sort of peer pressure among nations around them. There's a plan to meet every 5 years to renew those pledges, and an aspirational goal was put forward to limit temperature change to 1.5 degrees Celsius. For some perspective, this implies that the world goes to actually 0 greenhouse gas emissions by the year of about 2070. Okay, that would be a really dramatic turn of events if that comes about, but that's what's needed to get us to about 1.5 degrees Celsius. Paris relies on then the good faith of countries to follow through with their commitments, right? In the United States, that's basically the Clean Power Plan, as well as things like standards for mobile vehicles and things like that, that have been put into place over the past several years. But the biggest one is the Clean Power Plan. So the fact that the Clean Power Plan was rolled out before the agreement in Paris, that gave the US credibility to be saying that we can achieve our targets, and that gave other nations confidence to say that the US was going to take action and therefore that they would follow. So we talk about the Clean Power Plan sort of in the context often of the United States, but it's easy to forget that the Clean Power Plan really underlies a lot of what the global agreement. Without the Clean Power Plan, we might not have had the Paris Accords as they turned out. Okay. The consequences of the Paris Agreement for climate, these are emissions here, growing. Pledges are out to 2030. This is what emissions might look like in the absence of Paris. With the pledges, it brings us down by this much, if all countries follow through on their pledges. And then, of course, the goal is to continue that into the future, either with the continued ambition or an increased ambition. And what's shown on the right here are then the probabilities of achieving different temperatures for these different scenarios, right? Where here the world is really cooking, right, by by 2100, even in these cases down here, there's still some temperature change. And by the way, the aspirational goal of achieving 1.5 degrees Celsius, that's even given a 10% probability, even in this most aggressive reduction. Okay, so we've got a lot of work to do on climate. Okay, I'll sort of conclude with going back to some of the work that my research group does on now addressing climate change, but using sort of the same toolbox that we were looking at before. How does energy and emissions decisions that we might make, how do they play into emissions of air pollutants and therefore air pollution related human health effects? Okay, so a couple of examples, again from Raquel Silva. This is looking at the effect of climate change itself. So as climate changes, that affects meteorology, it affects emissions of pollutants from natural sources, for example, it affects atmospheric chemistry. These things then all affect air quality. So we can ask the question, if as climate changes, what would be the effect of climate change on air pollution and therefore air pollution related deaths? And that's what we've done here, using, again, a multi-model ensemble. And the results that we get here are, this is 11,000 deaths in 2030 due to changes in the ozone caused by climate change. And by 2100, over 100,000 deaths globally. For PM 2.5, 56,000 deaths in 2030, about 215,000 deaths in 2100. You notice that there's big uncertainty bars here. And this is brought about by the big spread of model results that we have from a lot of different models. Here it's, if I remember right, 7 of 10 models had a positive change. Only 3 had a negative change. And here it's all but 1 model show a positive change. So the fact that this is coming up with positive numbers that are fairly big, I think is, this is actually the first time anybody's used a multi-model ensemble to look at the effect of climate change on health on a global scale. And I think this is kind of a big deal. Where I'll end with is our work on co-benefits. And the idea of co-benefits is if we take action to reduce greenhouse gas emissions, those greenhouse gas emissions often come from the same sources as air pollutants. So taking actions, for example, we get people to drive less and ride buses more. That's good for air pollution. That's good for climate change as well. We replace coal-fired generation with renewable energy or even natural gas. That's good for air pollution, and it's good for climate. Okay? That's the idea of co-benefits. And we can then quantify the climate change, the air pollution and human health co-benefits brought about by taking action to reduce emissions. That's sort of the traditional way, actually, of looking at co-benefits. What we've done here is to acknowledge that changes in greenhouse gases will affect climate change, and that also affects air pollution, and therefore affects human health. So we're actually looking at this, accounting for both of these mechanisms by which greenhouse gas emission reductions might affect air pollution and therefore human health. So the approach that we have, I worked with an energy economics modeler, Steve Smith, and we're looking here basically at a difference between a reference case with no climate policy and one of the RCP scenarios, which is known as RCP 4.5. So consider that a pretty aggressive global climate change policy that addresses emissions from all nations and from all emission reduction sectors, okay, in the most cost-effective way. And the results that we get here, this is global population-weighted PM 2.5 going into the future. So from the present day, by and large, PM 2.5 is expected to get worse. On a global scale, it gets cleaner. We're already getting cleaner in the United States, but this is on a global scale. And and then the world turns the corner and starts getting cleaner. It's the difference between the blue curve and the red curve that's important here. And that difference is, by the time we get to 2100, 2 micrograms per cubic meter, multiply that by the global population, and that's a big health benefit. And that's what we see here, right? So we also did it for ozone. The estimates that we got from this, again, fairly aggressive global greenhouse gas mitigation policy are, for PM 2.5, 1.5 million avoided deaths per year by 2100, over 500,000 deaths per year by 2100 for ozone. Actually, the ozone comes out surprisingly big here. And one of the reasons is the greenhouse gas reduction policy reduces methane as well. And methane is affecting this global background of ozone. Okay? That brings ozone down. Okay. This relates to the talk on valuation. We then valued those lives saved. And so I used a high value of life, which is basically pegged to the US value, and the low value of a life is basically pegged to the values that are used in Europe today. So that gives the red and the blue with uncertainty around it. For comparison then, you can see the costs, which are in green. This is the cost of reducing greenhouse gas emissions in the first place. Cost per ton of CO2 reduced. Okay? The benefits here actually far outweigh, this is in 2030, the costs globally and for several world regions. It's really actually very striking for East Asia. East Asia, again, is basically China. The types of actions that China would take, likely, to address a greenhouse gas target would be to move away from coal. And we know that coal is exposing a huge number of people to high air pollution, especially in the big cities in China. And so the benefits for health far outweigh the costs of greenhouse gas emission reductions in the first place. In 2050, that's also the case. The costs now are creeping up. By 2100, I should say, this is the cost as estimated by 13 different global energy economics models. So I put the solid line here as the median of those, and the dashed lines are the range of those models. Okay? By 2100, the models disagree quite a lot on what those costs are going to be, right? So we don't really know by 2100 what it's going to cost to reduce greenhouse gas emissions. And so the models are disagreeing a lot. But basically, we've taken advantage of the very cheapest ways to reduce greenhouse gas emissions over here. And we're stuck with now relying on other methods to get further reductions, okay? Okay, so an important finding. And the other thing that was important here, you can compare our estimates of co-benefits with the entire literature on co-benefits, which is given by the range in yellow here. And you see, by and large, our results are higher. And there's a few reasons for that. One is we're using a global model, so we're not, and we're looking, most of the literature looks at regional co-benefits, okay? So the effect, co-benefits within one country. But you might remember at the beginning of the talk, I said that ozone pollution from the United States actually kills more people outside of the United States than within, okay? So with that being the case then, now with our global model, we're able to account for these international transport of air pollutant that becomes very important. We're also projecting population growing, susceptibility to air pollution growing in the future, and the economy is growing, and that drives valuation up as well going into the future. Okay, so we're accounting for a lot of factors that previous studies have sort of overlooked. One of the exciting things we're doing with this now, this is the work of Yuchang Zhang, who completed his PhD with me just a few months ago and will soon start working with the EPA. We did what's called downscaling of this co-benefit study to the United States to understand at a finer scale what these co-benefits look like for the United States, both for air quality and then for health. So you see the maps here of PM 2.5 and ozone. You might notice this ozone map is actually very smooth, not showing much indication of effects of changes in local sources. And what we did then was actually pretty neat as well. We separated out the co-benefits into contributions from domestic reductions within the United States versus the foreign reductions, which include methane reductions on the global scale. So for ozone, I have to orient myself. For ozone here, most of the reduction actually came about from the foreign emission reductions rather than the domestic reductions, and we think that's an important finding. For PM 2.5, it was overwhelmingly the domestic emission reduction, but the foreign reduction still had contribution to the total reductions that, again, might be overlooked by other studies that focused on the regional scale. When we did avoided deaths within the United States then, this is using BenMap, many of you know that program. Domestically, we get 21,000 deaths per year avoided due to reductions. This is for PM. So the domestic is greater than the foreign for avoided deaths. But for ozone, the opposite is the case. The foreign emission reduction is actually more important than than the domestic emission reduction. Just to wrap this up then, looking at co-benefits within the United States, these were the numbers that we got, again, from a pretty aggressive global policy or global action to reduce greenhouse gas emissions. We also worked with Ying Li, who did estimated for these scenarios the avoided heat stress mortality. She actually comes up with a number that's an order of magnitude smaller than we found from the reduction in air pollution, and that was kind of interesting. So the monetized co-benefits for the United States, applying a value of a life again, at a low VSL, $74, at a high VSL, $220. Those are we focus here on the year 2050. And this finding that foreign greenhouse gas mitigation is important for the total avoided deaths or total co-benefits that we receive in the United States, I think is pretty important. It shows that previous studies that focus regionally or nationally may be missing an important part of the total co-benefits. But it shows as well in the international political realm that the U.S. can gain perhaps significantly greater co-benefits, especially for ozone, by collaborating with other countries to combat climate change. So by engaging with other countries, the air quality and health benefits that we achieve here in the United States are actually going to be higher. And I think that's contrary to how people have approached this problem in the past, that climate is a global problem, air pollution is local. And we're suggesting, well, that's not quite right. Okay. And I think that's a good place to stop. So thanks a lot for your attention. I'll be happy to take questions if we have time.
One or two questions, and then we'll break for lunch. Right here.
So there was almost no mention of population in the Paris Climate Agreement. And if you plot population versus carbon emissions, prior to 1990, it's going up about 1% for every 1% increase in population. And then after that, it goes up at 4% from 1999 on. So it's really increased, mostly due to China. So, and these trends are, with population versus all these emissions and things, are very linear for over 100 years. What do you think on the prospects there with regard to that?
Yeah, it's a good question. I've sort of thought to myself before that if we had been meeting like this in the 1970s, we probably would have put population as the first topic and then climate change and air pollution as sort of subtopics beneath that. And I think changing our approach to it all has changed quite a lot, right? In the international sphere, it's not been seen as a good thing for one country to be telling another what they ought to be doing about their population. And so I think that's by and large the reason why that hasn't gotten a lot of traction is just the impracticality of either controlling population or of international negotiations where you talk about population control. Yeah. I'm not sure I've addressed your question.
Over here.
I know that you were modeling based on ozone and the particulate matter, but now that the ice caps are melting, there's methane that's actually coming out. It's been hidden for years as far as that's concerned. The sea level is rising and will continue to rise, and therefore there will be migrations northward, which means cutting down of forests, increase in global warming as a result of that. Has anybody looked at any of this data tied in with what you're presenting here?
I don't think anybody's quite put it together the way you have. You have suggested, I'll say.
I mean, that's just the tip of the iceberg.
Yeah, I mean, a lot of changes can happen globally. In climate change, a lot of the state of science is trying to understand these individual interactions and then try to put it together into a big story like that. You mentioned methane release from the Arctic, and that's sort of one of the big wild cards of, it could be very big, but it could be very small. We see some suggestions that it's happening now, but it's hard to quite quantify what that influence is. So I think, it's worrisome, but on the other hand, we don't really know that it's going to be one of the big influences.
But your projections are basically based on the fact that the population remains in place.
That's right, yeah. We have, different population growth in different regions of the world, we don't have the global population responding to climate change yet. That's sort of another level of sophistication beyond what we've been able to do.
Okay, thank you.
Sure.